Hello, everyone. Welcome to part 6 in our series on distributed word representations. This can be considered an optional part, but it's on the irresistibly cool idea of retrofitting vectors to knowledge graphs. Here are our central goals. On the one hand, as we've seen, distributional representations are powerful and also easy to obtain, but they tend to reflect only relatively primitive semantic notions like similarity or synonymy or connotation or relatedness. So that might feel limiting. On the other hand, structured resources like knowledge graphs, while sparse and kind of hard to obtain, support really rich learning of very diverse semantic distinctions. So the question naturally arises, can we have the best aspects of both of these? And the inspiring answer given by retrofitting is yes, we can combine them. The original method for doing this is due to this lovely paper, Faruqi et al. 2015, which I'm going to be giving a brief summary of in this screencast. So here is the retrofitting model. It consists of two sums, and they constitute kind of opposing forces. Imagine that we have an existing embedding space like glove or some embedding space that you built yourself. That's Q hat. And we're learning these QIs and QJs. The term on the left is basically saying, remain faithful to those original vectors as you learn these new vectors QI. Try not to be too dissimilar from where you started. That pressure is balanced against the pressure on the right, which is saying, make representations that look more like the neighbors for the current node in the knowledge graph, which is, defined by this set of relations E. So two opposing pressures. On the one hand, we're saying be faithful to the original. On the other hand, we're saying look more like your neighbors in the knowledge graph. If we set alpha to 1 and beta to 1 over the out degree for the node that we're targeting, then we have basically balanced these two pressures. If we set alpha really large, we'll mostly want to stay faithful to the original vectors. If we set beta comparatively very large, then we'll mostly want to look like the neighbors in the knowledge graph, and we won't remain so tethered to the original embedding space that we started with. This illustration kind of nicely depicts what happens in the model. The gray vectors are the original embedding space. We have this knowledge graphs that connects the associated nodes, and because they're connected in the retrofitting space, which is given in white, these nodes are kind of pulled together and look more similar. There's a bunch of code for doing retrofitting in the course repository, and I'll just show you a few quick illustrations using that code. Let's start with a simple case. We have a very simple knowledge graph where node 0 is connected to node 1, and node 0 is connected to node 2, just directionally. What happens when we run the retrofitting model is that 0 is pulled equally close to 1 and to 2. Kind of equidistant between them and closer to both than it was in the original embedding space. Here's a situation in which every node is connected to every other node. That's represented on the left here. That's where we start. And as a result of running the retrofitting model with alpha and beta set in their default parameters, what happens is that triangle just gets smaller in a kind of fully symmetric way as the nodes become more similar to each other because of the graph structure. Here's a kind of degenerate solution. If I set alpha to 0, I have no pressure to be faithful to the original vectors. All I care about is looking like my neighbors from the term on the right. And as a result, all these vectors shrink down to be the same point after the model is run for a few iterations. If instead I had done the opposite of made alpha really large comparative to beta, then basically nothing would have happened in the learning, and the triangle would remain its original size. It's worth considering some extensions. So I think the fundamental limitation of this model is that it is kind of assuming right there in its objective that to have an edge between nodes is to say that they are similar. But of course, the whole point might be that your knowledge graph has very rich edge relations corresponding to different linguistic notions like antonymy. And we certainly wouldn't want to treat synonymy and antonymy as the same relation and just assume that it meant similarity in our model. So there are various extensions. I think the most general extension that I've seen is from a paper that I was involved with, led by Ben Linguistics, which is called functional retrofitting, which allows you to very flexibly learn different retrofitting modes for different edge semantics. And once you start down that road, you have a really natural connection with the literature on graph embedding, that is learning distributional representations for nodes in knowledge graphs. And this paper led by Will Hamilton is an outstanding overview of methods in that space. And then you have this nice synergy between NLP methods and methods that are more associated with work on knowledge graphs and social networks and so forth. And finally, here are some code snippets, just showing some simple illustrations of the sort that I showed you earlier in the screencast. And I would just mention at the end here, if you would like to apply these methods to WordNet, which could be a powerful ingredient for the first assignment and bake-off, I would encourage you to check out this notebook, BSM 03 Retrofitting, because it walks through all the steps for doing that.